Welcome back, Math 168 students. This is section 6.2, distribution of a mean. In this chapter, we'll be finishing up our chapter 6 for this current term, and then we'll be moving forward to our last examination of the term. So I'm going to just switch over. First, I'm going to get rid of this, get me out of here, and try and work from a couple of clear screens here. You need your graphing calculator. You'll need your slides, and most appropriately also you'll need your formula sheet also. Okay, so let's see what we can do here. So let's talk the basics first. So if we're talking about a CLT for a mean, so first of all, we're talking about a mu value from a population parameter now distributing itself down to an X bar value for a sample set. And if we talk about the CLT, the central limit theorem for a mean, it discusses that as we have a greater sample size, as you can see, as n develops from 10 to 30 to 50, we realize that we have a better distribution of the sample means. In other words, as the larger the sample size gets, as we've seen in the past, the smaller the standard error, the less spread we will have from the center of the data. And we see that clearly. As n is 10, then we are somewhere between a 1 and a 3.2. As n is 30, well, we're somewhere between a 1.5 and maybe now a 2.75, or maybe even a 2.5-ish. But as we get closer to 50, we see that truer center coming into our being. We're no longer at 2, we're no longer at 1.8. Now we're clearly at a 2.0 for a center value. So again, the central limit theorem will tell us in a mean value that the more n values we have, the more plausible we can trust that the distribution of the sample means is accurate. Okay, so let's jump to the next slide. Oops, hold on one second. There we go. So we have a standard error formula for sample mean x, and in that standard error, we are going to take the standard deviation, sigma, and we're going to divide it by the square root of the sample size, n. So in this particular case, it gives us some data. And it says, if a random sample size of 1,200, so right away we know that we have a sample size of 1,200. And it says, are drawn from a population with a mean 29 and a standard deviation, standard deviation of 7. Standard deviation of 7, so my sigma is 7. Find the standard error. So we want the standard error. And if we want the standard error, we're going to take the sigma value, 7, and we're going to divide it by the root of 1,200 to see what the sampling distribution or the standard error will be from this value. So if you take 7 and you divide it by the square root, sorry I didn't have this already. And I'll do my calc if you want. Actually, let me open this up for you. How about this? Clear everything. Much better, right? So I'm going to take 7. I'm going to divide it by second square root, and it was 1,200. I'm going to get a sampling of about 0.202. So we have a standard error of about 0.202. And remember, this would be my distribution. And if we were distributing from a center, and it did say that we had a mean of 29, so if we were distributing from a 29, we would be going plus 0.202 and another plus 0.202 to get 2 standard deviations up, and would be minus 0.202 and minus another 0.202 to get 2 standard deviations down. The standard error is one movement in from our center to a position, and then another movement to another position. So the central limit theorem for x bar, if n is sufficiently large, we'll discuss that in this slide, then we can distribute our value or our statistic x bar. It will be normally distributed from a center mu and a standard error of sigma divided by n. Remember that when we discuss these things, that we are always distributing normally from a mean and a standard deviation. And for us, the mean is mu in this formula. And for us, the standard deviation is the standard error, and the standard error is the standard deviation divided by the root of n. So this is our middle, and this is our distribution. And that's what we mean when we say that we will normally distribute those items and we'll use the x statistic that we have and we'll normally distribute it from here. A normal distribution is usually a good approximation as long as n is greater than or equal to 30. It says smaller sample sizes may be sufficient for the symmetric distributions, and 30 may not be sufficient for a very skewed distribution or a distribution with high outliers. So the standard error for our formula says that we're going to take sigma and divide it by n. But we generally don't know sigma, but what we do know is we know the standard deviation. Okay, so we're going to replace the population standard deviation sigma with the sample standard deviation s. We will know that number. Secondly, replacing the sigma with s changes the distribution from a z statistic to what we call a normal t distribution. Okay, you're familiar with this t value or this z distribution. We've done the z's. Now we're going to also do what's called a normal t. Now, the only reason we're using a normal t is because we took out the sigma and we put in the standard deviation. So when you switch to a single mean and you're using a standard deviation, you're going to have to use a t distribution. And all we have to do is use a different part of the calculator to find the t distribution. It says the t distribution is very similar to the standard normal, but with a slightly fatter tail to reflect the added uncertainty. I'll show you that. So this is a picture of both the normal distribution in black and the t distribution in blue and in red. Okay. Now it says the t distribution is characterized by its degrees of freedoms, df. You will hear that df term quite often. The degrees of freedom are related to the number of items n in the sample size. It says degrees of freedom are calculated based on the sample size, and to tell you right now, they're always one smaller than the actual sample size. So if the sample size is 70, then the degrees of freedom are 69. If the sample size is 15, then the degrees of freedom are 14. The higher the degrees of freedom, the closer the t distribution is to the normal. So if you take a look at the red degrees, we have a T5. We have 5 degrees of freedom, which means we had 6 things in a sample. You can see how the tail is much fatter out here, a little higher than the normal distribution of black. And you can also see that it's lower than the normal distribution. It's not quite high enough. But you can see as the degrees of freedom go up to 15, that the blue gets a little closer to the black line, and the blue also comes down closer to the black line. The higher the degrees of freedom, the closer that this distribution is to the normal or the standard normal distribution. In other words, higher degrees of freedom are better, just like with larger sample sizes. Absolutely no different. Here's a good slide that you should study that'll just change or the disparities between the normal distribution and the t-distribution. So first thing it says is the standard normal is the most common normal distribution with a mean of 0 and a standard deviation of 1. We know that, 0, 1. We've been using that in all of Chapter 5 and Chapter 6. The t-distribution can be thought of as the cousin to the standard normal. It looks similar. It is centered at 0 still. There's no change there. It has a basic bell shape, but it is shorter. It never goes over the 0, 1 distribution. And it is flatter around the center, and the standard deviation is proportionally larger than z, meaning the tails on the outside are always a little larger. If I go back, meaning these tails here will always be above the normal distribution, and the height or the maximum, the apex here of the t distribution will always be lower. This will always be inside, these will always be outside. Always that way. It says the t-distribution is typically used to study the mean of a population. If the population has a normal distribution or fairly close to it, its role is especially important. If your data set is small, or if you don't know the standard deviation of the population sigma, which is when we use S or the standard deviation. Each distribution is distinguished by what the statistic is we call the degrees of freedom, okay, DF. In situations where you have one population and your sample size is n, the degrees of freedom is the corresponding t-distribution is n minus 1. Like I told you before, if you have a sample size of 10, then your degrees of freedom are 9. If you have two different populations, if you have a population of 12 and a population of 7, then you will always use the smaller of those samples. So you go to the 7, you will subtract 1 and have degrees of 6. Always use the smaller sample size. Normality assumptions. So in using a t-distribution requires that the data comes from a normal distribution. So it has to be normally shaped. The assumption is about the population and not the actual distribution of the statistic. So we're speaking about the mu value here. We're not speaking about the x-bar distribution. We have to know that the data is normally distributed. For large sample sizes, we don't worry about this because S will be a good estimate of sigma and the T will be very close to 0, 1. The only time we worry about a large sample is if it was heavily skewed with many outliers. For a small sample size less than 30, we can only use the t-distribution if the distribution of the data is approximately normal. So that tells us if we have smaller sample sizes under 30, as long as we see a distribution that is fairly normal, we can use the t-distribution. The normality assumption gives us a problem, though, at the same time. And this problem is that for sample sizes, it's very hard to tell if it actually is normally distributed. There's a number of different sample sets, and these sample sets are of size n equal 10. And it's very difficult to look at them other than maybe one or two and say, you know, this is normally distributed, this is not normally distributed. That's a tough call. So we have some protocols in place we're gonna do here and make it happen. So let's say the sample size is small, and we're going to use this t-distribution. If the data looks reasonably symmetric, again, you can't be real picky here, and that should say does not, and does not have any extreme outliers, even then, remember, it's just an approximation. This is just an estimate. And what we're calculating here is the distribution of t. How far will it go from the center outward? In practice or life, you should just run simulations like stack heap, bootstrap, randomization. Okay. It says not all TI graphing calculators support T-star. Well, I think most do nowadays, and the calculation is still under second vars, and it's called the TCDF. So if we go to second, and we go to vars, and we've already used normal CDF, well, now you can notice that we have number 4, an inverse T, and number 6, a TCDF. This will be our T value with TCDF. And if I'm looking for endpoints of T, I can use inverse T. Okay, so number 4 and number 6 will be the ones that we use for t-values. And you can see we can find TCDF by doing a lower, an upper, and a degrees of freedom. So if I were just to play with this one for 1 second, number 6. So you can see we have a lower again. I'll use E199. Let's say the upper that distribution that I have is, I don't know, let's say 17. And let's say I have degrees of freedom. Let's say this came from a set of n equal 9. Well, if it's a set of n equal 9, then degrees of freedom are 8. And remember, I'm calculating area here. So that my area calculation, I actually have very high area calculation from -1 E99 up to 17 on my distribution. I would have this, remember, I would have a 99 percentile. And these are just numbers to put in. Let's go to the next one. So let's say that we have a problem here, and this is Wiley, and this is, I'm not sure I can tell you this is actually Wiley question 2, 3, 6, those kinds of things, but I can tell you we can try these though. So it says, the t-distribution is an approximate model for the distribution of a sample means only if the sample size is greater than 30 and also underlying distribution is approximately normal. So it's asking us if this is the model that we would use. Well, remember the model was that if the sample size was greater than 30, we could use it. If the distribution was approximately normal, we could use it if it was under 30. So to say that we need to be 30 and we also need to be normally approximated is not what we're talking about here. This would be a false statement for number 1. False. I can't really do it. I'd like to do it, but I can't seem to do it. In second one, if sample size n equal 50 is heavily skewed with outliers, and then the t-distribution is not an approximate model for the distribution of a sample means. You got to watch the knots, right? We have n equal 50. We are allowed to be skewed with an outlier. If we would normally talk about this, then we would say that I can use this model. Well, this is not an appropriate model. So it is false to say that this is not an appropriate model because it is an appropriate model if you have an n size greater than 30. So the answer here again would be false for the second one. If a sample size n equal 10, so now we have a low sample size of 10, heavily skewed with outliers, then t-distribution, not a model. This is true. It's true because we can't be heavily skewed and have a sample size of 10, but we can be heavily skewed and have a sample size of 50. So for the third one, my answer is true. What are the endpoints of a 90-degree confidence interval level of a t-distribution, with a t-distribution with degrees of 15? Okay, so think about what we're doing here and what we're calculating. So first of all, we have endpoints of a 90%. So we want the n's. That's important, that we want endpoints. And of those endpoints, I really wish I could get this thing to give me a little bit better focus because my focus is really off today on my, put my pen here. Hopefully it focuses in. So I want these endpoints and I'm dealing with a 90 percentile. Okay, so 90 percentile, which means on each side, I'm going to have, on this side, I'm going to have 0.05. And on this side, I'm all going to have, so I'm going to have 0.05. Because 5% here and 5% is 10%, which leaves me 90% in the middle for the distribution. My degrees of freedom are already given to me to be 15. So I'm going to want to go to my calculator. And in my calculator, I'm going to go to my second vars. I'm going to want to use, remember what we're trying to find here. is we are looking for the endpoints. Okay, so we want an inverse t, number 4. The inverse t, I'm going to use a 0.05. I know my degrees of freedom are 15 because it told me that was the degrees of freedom. It didn't say that was the n, it said that was the degrees of freedom. And when I paste that, I get negative 1.753. Negative 1.753. Remember, for every positive or for every negative, there's also a positive. This is the positive one, negative 1.753, and this is the positive 1.753. These are the endpoints for a t distribution with degrees of freedom of 15. Second question, what is the area to the right of endpoint 2.50? Okay, so now we're changing slightly. So now what we want to do is we want to talk about the endpoint. And so now, or we want to use an endpoint to get a value of an area. So it's the area to the right. So again, I'll sketch this out. So we're centered up here. Remember, even t distribution center up at 0. We're at the right of a 2.5. 2.5. And we want the area going to the right. So again, calculator. Second vars. Now, this is an area calculation, and it's a t, so it's a TCDF, number 6. Your lower number, 2.5. Your upper number, 1E99. And your degrees of freedom were exactly the same degrees of freedom at 15. And that's going to give me an approximate area of 0, 1, 2. So approximately 0, 1, 2. If I'm calculating that into area as a percentage, then it's approximately 1.2%. But as a decimal, this is my value. And remember, this is my p, right? That's my p value because it's the amount of area encompassed from the point 2.5 going to the right with degrees of freedom of 15. Question number 6. Assume the sample is a random sample from a distribution that is reasonably normal and distributed. And we are doing inference on a sample mean. Find the endpoints of a t distribution with 5% beyond them in each tail if the sample has size of 8. Okay, well, I'm going to just, again, I like to draw it out kind of quickly. So I'm looking for endpoints. I'm looking for this endpoint and this endpoint. It says that I have 5% in each tail, 0.05, 0.05. And I know that my n size equals 8, which means that my degrees of freedom equals 7. Okay, so we got to know that when we're given n versus when we're given degrees of freedom. Okay, so let's go calculator. All we have to do is find the left-hand side one here. Vars, we're going to use, we want the endpoint. We're going to use inverse. We're going to use an inverse norm, but an inverse norm for a t value. So we're going to use number 4. The area is 0.05, 5%. The degrees of freedom are 7. I'm going to paste that in. And we get a negative 189. That would be an 895. So we're going to get a negative 1.895. And wherever you get a negative, you'll also get a positive. Confidence interval levels. So now we're moving away from a specific part and getting into a more generalized part here. The general formula for a confidence interval level is the sample statistic plus or minus z star times the SE. And we see that from our formula, our generalized formula right here. The generalized formula for a confidence interval level is the sample statistic plus or minus z star times the SE. For means, we will replace the sigma value with S, which will cause us to use a t-distribution instead. So it'll be the statistic plus or minus t star times the standard error. Okay, so we're because we're taking out the sigma and we're putting in the standard deviation, we're making this change. And we know that the statistic here is really the x value because that's the statistic that comes along with a distribution. Statistic right here will be an x bar because that's this part that comes along with the statistic for a mean. It says if the population is approximately normal or the n value is greater than 30, then a confidence interval for mu can be computed by using, and it gives us that formula. Okay, well, that's the same formula that is right here. Single mean, confidence interval level, x plus or minus t star, and we know how to find t star now, multiplied by the standard deviation divided by the root of n. Pretty simple formula compared to some of the other ones that we've already been using. And move to the next slide. Use the t-distribution to find the confidence interval level for mu given that the relevant sample results give the best point estimate for mu, the margin of error, and the confidence interval. Assume that the results come from a random sample from a population that is approximately normal. Okay, so we have what we need telling us that, hey, you know what, this is approximately normal and you're okay. Let's scoot this down just a little bit right there, I hope. I hope that works out better for me. I'm just not sure why my camera is so fuzzy today. So we have a 90% CI. Mu using the sample, here's our sample, x bar at 2.6. We have a standard deviation at 0.4, and we have n equal 100. Okay, this will be straightforward. This will be nice for us. So first of all, our point estimate. And I'm going to answer these on the paper because it's a little bit easier for me to answer them on the paper. Our point estimate. Well, our point estimate is 2.6. 2.6 is the number that we were given. That is our x bar, and that's our best point estimate. What is our margin of error? Okay, well, remember, margin of error comes from the back side of the formula. The formula that we're utilizing is x bar plus or minus t star, where t star multiplies itself against the standard deviation divided by the root of n. That's the formula we're using. And this component right here is the measurement of error. Okay, those two combined. So when we combine those two, first of all, we need the t star value for this calculation. So let's go get the t star. Remember t star, I'm going to clear everything out here. T star is an inverse value. It's an inverse t. Our area we are dealing with, the problem says, is a 90%, excuse me. So it's 0.05 on the left tail. The degrees of freedom are 99. I got that because I took 100 minus 1. N was 100. I took away 1. That's 99. And I'm going to get my t star value. So my t star value is 166 plus and minus. So first of all, I now know that t star right here is 1.66. I'm going to multiply that by, I know the standard deviation from the problem is 0.4. And I know that the root of n is actually 10, but I'm going to write root of n right there. I'm going to do those calculations, and when I'm all done, I'm going to get 0.07 for my margin of error. This calculation made my margin of error. So now for my confidence interval level, I'm going to take my original data point, 2.6, my statistic, I'm going to add and I'm going to subtract my measurement of error, 0.07, and I'm going to get a confidence interval level that goes between 2.53 and 2.67. This was ultimately my CI that I was trying to find. And from that, and I only needed two basic parts. I needed the point estimate, and I needed the ME, and the ME, from the ME, I needed to go find the Z star. or the t star, sorry, and the t star, and from that t star, I then multiplied it by ultimately the standard error. A lot of words, right? This one has been on final exams for several years, so I would know how to calculate this particular problem. Domestic cat kills many more wild birds in the United States than scientists thought. This is the article statement. Researchers used a sample of N equal 140 households in the U.S. with cats to estimate that 35% of household cats in the U.S. hunt outdoors. A separate study used what was called a kitty cam to record all activity on 55 domestic cats that hunt outdoors. The video footage showed that the mean number of kills per week for the cats was 2.4 and a standard deviation of 1.51. Find a 95% confidence interval level for the mean number of kills per week by U.S. household cats that hunt outdoors. Okay, so a couple of things. First of all, I see an N equal 140 and I see an N equal 55. Well, remember, we're doing a calculation of the sample data, okay? And we're using it for the population. So for us, N is going to be equal to 55, not 140. That was the population N. That was the 140. We are also going to use X bar at 2.4 because that's what it says that the average is, and the sample S, so we don't have a sigma, we have a standard deviation, is 1.51. We're going to have to get a t star, and that t star is going to be calculated for a 95% confidence interval level, so that means 2.5% on each side, with a degree of freedom of 54, because that's one less than the 55. And if you do your calculator and you go find that, remember, 2.5% on each side, you're going to get a t star of, let's go get that. Second, vars. We want an inverse t. We want 0.025. We want degrees of freedom of 54. And we get 2.005. So 2.005 at 3 decimal places. Remember, that's a plus and a minus. So we're going to take our X bar. X bar is 2.4. We are going to add and subtract T star, 2.005. But we're going to multiply that by S, 1.51, divided by the root of 55. When we make those calculations, 1.992 to 2.808. So we have a 95% CI between those two numbers. So the margin of error is T star times S divided by root of N. Now, if we do a little bit of algebra here, and we've done this before in the past, to solve it for N. So if we're looking for the sample size itself, you can see that ultimately it turns into that the N value, if you want some N value, then you would take Z star multiplied by the standard deviation, divided by the measure of error, and you would square that formula. This would give you the N range itself. Makes a plausible guess for how big that is. Now that is also given to you in your formula sheet. Make sure you understand right here. Means, and the exact same formula is sitting here. It says estimate the sample size. So it says what population, what sample size is needed. So it's asking us for the N value. If we want a margin of error within plus or minus 13, and we're estimating a population mean of 90%, assuming that the previous sample had S of 150. Okay, so first of all, we want to utilize n equal z star times s divided by the measurement of error square. So first of all, we need z star. We need z star for a 90%. And again, remember, 90% means 5% on each side. We already did this calculation. It's 1.645. If you need to go to your calculator, do the inverse for this value. And when you inverse this value, you'll get this, okay? 1.645. I need that value. I need it multiplied by the standard deviation, and the standard deviation, or the S value, sorry, the S value was 150. And I need to divide it by the measurement of error, and the measurement of error was given to be 13. And don't forget that value has to be squared. Make sure in your calculator you put all of that in there just like that. It also says we should round up to the nearest integer. So I need, first of all, I need a parenthesis so that I get a fraction. And in that fraction, I need 1.645. I need to multiply that by 150. I need to divide that by 13. I need to close my parenthesis, and I need to square that value, and I need to get rounded up to 361, because it said to round up. It didn't just say round, it said round up to the nearest whole integer, 361. Almost done. So if we're doing a t-test for a single mean, and again, I'll bring your attention back to your sheet, single mean, confidence interval level, test for testing statistic. We're going to take the sample, x, that's our sample. We're going to minus the null, and we're going to divide it by the standard deviation divided by the root of n, which is really our standard error. Now notice it says on our paper that if the population is approximately normal or if n is greater than 30, then the p-value can be computed as the area in the tails beyond t of a t distribution with n minus 1 degrees of freedom. So we're doing all the same things that we've been doing just now. First question. Use the t distribution and the sample results to complete the tests of the hypothesis. Use a 5% significance level, so that means 2.5% on each tail. Assume the results come from a random sample. If the sample size is small, assume the underlying distribution is normal. So they're giving us all the parameters we need. So we have a test of H sub O at mu of 10. So we know the null value is 10. We are using a sample statistic of 13.2. And we have a standard deviation of 8.7 with a sample size of 12. Give the test statistic. Okay, so we're going to use t-test is equal to x bar minus the null divided by the standard error, which is really s divided by the root of n. All these are very easy to find in the problem. Our x bar is 13.2. Our null value, nothing going on, mu equals 10. It says it right in the problem. Our standard deviation was 8.7, and our root is of 12. Our sample size, 12. Make sure you put that into a calculator. Make sure you give a fraction bar and a fraction bar, and you can do that pretty easily. So you enter a fraction. In the numerator, we need 13.2 minus 10. In the denominator, we need another fraction, so we enter another fraction. We put in 8.7, and we put in the root of 12. And then we let the calculator do the math, 1.27. So let's go back to where we are. So let's know what we have right now. Right now we have a curve, and we know that the t number, is 1.27. Remember, the area beyond that, the p-value represents that. So we have to go calculate a TCDF. We're going to find the area with a minimal number of 1.27 going to 1E99 with 11 degrees of freedom. We're going to go to our second FARS. This time we're going to go to number 6, TCDF. Our lower, 1.27. Our upper, 1E99. And degrees of freedom, 11. And we're going to find something at 0.115. 0.115. Remember, that's our p-value for this question right here. What is the conclusion? Well, the conclusion is do not reject. Why don't we reject? The p-value is greater than the alpha. There's no way we're rejecting a 5% significance level when we're at 115 for a p-value. We're doing all the same things we did, but now we're finding them a little bit differently. One more, last one. It says, be nice to pigeons. In a study conducted in France, equal amounts of pigeons were spread, pigeon feed was spread on the ground into two adjacent locations. The person was present at both sites. One was acting hostile and running at the birds to scare them away, and the others were neutral and just observing. The two people were randomly exchanged between the two sites throughout, and the birds quickly learned to avoid the hostile person's site and to eat at the site of the neutral person. At the end of the training session, both people behaved neutrally, but the birds continued to remember who was hostile. In most interesting part of this experiment, the two people exchanged coats, orange wore by the hostile and yellow wore by the neutral, throughout the training. The pigeons were not fooled and continued to recognize and avoid the hostile person. The quantity measured that the difference in the number of pigeons at the neutral site minus the hostile site was n equal 32 measurements. The mean difference in the number of pigeons was 3.9 and the standard deviation was 6.8. To see if this provides evidence that the mean difference is greater than 0, meaning that the pigeons can recognize the faces. State the null hypothesis, give the test statistic, state the p-value, and have the conclusion. Well, first of all, we have, let me get this down here. First of all, we have n equal 32. We need that. We also have an x statistic at 3.9. We also know that our standard deviation is 6.8. And our degrees of freedom are 31, one smaller than 32. So our H sub O is mu equals 0, nothing going on. Our H sub A is that mu is greater than 0, because we want to see that there's a greater difference in the two. So that's part A. Part B, we need it as part A. I'll label that part A. Part B, well, we're going to take our statistic, 3.9. We're doing our test value right now, our t number. We're subtracting 0. We're dividing by 6.8, and we're dividing that by the root of n, not df, n at 32. When we do that test statistic, you should get 3.24. Now remember what that means. Here's 0, here's 3.24, and here's the area beyond. You still have to find the p-value of the area beyond the 3.24. So we're going to calculate a TCDF. That TCDF is going to start at 3.24. It's going to go to 1E99, and it's going to use 31 degrees of freedom to calculate it. If you go calculate that, you get a p-value of 0.001. 1. What should we do? We should reject H of O because we find significant evidence that pigeons can recognize faces. Congratulations, folks. That is the end of this section. And our next discussion will be about getting ready for the final examination. Have a great day.